Hi everyone, we are now working in 3.7, section 3.7, and this section is about polynomial and rational inequalities. So we're going to take some of the ideas that we've done in the past of this chapter and apply them now with an inequality and talk about how do we solve these inequalities when they're not linear. We've done linear ones in the past, way back in, I think, the prerequisite chapter. But here we're going to make it a little bit more difficult and talk about polynomials with inequalities. And it is a rather difficult task, but I'm going to just jump right into some of these examples, and hopefully through the examples can explain as I go my thought process and how to do things, why I do them, and so forth. So this first example, I have x squared is greater than x plus 12. And I'm going to do this one actually in two ways, because although you can't do all of them two ways, it is, well, you can, but sometimes graphing both sides is not an easy task to do it accurately. So this one I kind of want to do, and I do it two ways because then I can show you that they do mimic each other. So first of all, the way I'm going to do this one is I'm going to look at each side separately, and I'm going to do these graphically. So I'm going to look at x squared, which we all know is our beautiful quadratic with a vertex at the origin, and we could graph some problems there as well. So this is x squared, so this is y equals x squared sitting right there. And this side is x plus 12. Well, that is a straight line, slope of 1, with a y-intercept of 12. So I'm going to kind of rough sketch it in here. I'm not going to put any scale on here, because let's just say 12 is here, and a slope of 1 means it's going up 1 over 1, so it's going upwards. And there's my straight line. Now we need to know where our x squared, where this guy is greater than this guy. So we're talking about larger. So in terms of our graph, we're talking about larger being a bigger y value, meaning looking at it above. So we want x squared is above x plus 12. And I see that, so as I'm reading from left to right, right here my line is below this x squared curve. But as soon, my line, yes, is below the x squared curve. Then it switches from the curve being below the line, and then again the line is below the curve. We want to know where x squared is above or the line is below. So that happened from this point this direction, and from this point this direction. Now, since I wanted a strict inequality, we are going to not include those values, but I need to know where that happens. And then we'll write our answer in interval notation. So our interval notation will look like a negative infinity till we hit that point with a round bracket, because we do not want the, we want a strict inequality, not an equal to in there. And then we want to union that or combine that with, from this point, not including it, up to infinity. And now we have to find those two values. And to do that, that's where those two pieces were equal. So we need to solve this equation, find out where those two things are equal. This is a quadratic, so quadratics, the method to solving a quadratic is to get all of your pieces on one side. So I'm moving everything that I need to over and setting it equal to 0. And then we either factor it or go to the quadratic formula. This one does factor nicely. And by now you guys should be pros at factoring. If not, keep working on it, keep getting some extra practice. And to get that 12 is going to be 4 and 3, and a minus with a plus. So now we set each one of those factors equal to 0. And again, we have done this through this entire chapter. So it is equal when x is equal to 4 and x is equal to -3. So this would be 4, and here would be that -3. So in our answers, we'd see it being in that region. So there's one method to graphically do that. The other method is starting again. This required us to be able to graph both sides. And a lot of times that is not something we know how to do. So I'm going to put all of it on one side. So moving everything. And if you remember, adding and subtracting things does not change our inequality, only multiplying or dividing by negatives. So I'm going to put this all on one side. Now this is a quadratic still, and if I were to graph it, it would be a U shape of some sort. And we did spend a lot of time graphing polynomials in this chapter. And the method we used was we found our zeros, plotted them, and then we did test points. So to find my zeros, I'm going to again have to factor it. And I want to know where this guy is greater than 0. So then we would put those things on a number line. So here's my -3, and here is my 4. And I knew if I were graphing it that those would be zeros. So if we wanted to graph it, it would be zeros. It would have some sort of, I should probably put the y-axis in here, some sort of y-intercept down here somewhere. I don't know exactly where it is. Yeah, I do. It would be at -12. And then we'd have our curve in there. Okay? And I know that this guy opens upward. And it would look somewhat like this. It might go down a little further in the middle. It probably does because that center is going to be symmetric and all of that. So my picture is off. But the idea is we just want to know where it is greater than 0. And now in chapter 2, we talked about a function, some sort of curve, being greater than 0, meaning it is above the x-axis. And this one is above the x-axis here and here. And we want to not let it be equal to 0, so again, -infinity to -3 and 4 to infinity. And this one I could do relatively easily because it was a parabola and I knew that it opened upward because the leading coefficient is 1, which means it opens upward, and we talked all about that at the beginning of chapter 3. But we can do this idea even more when we have something a little bit more complicated. So I'm going to do another one here on this video that's a little bit more complicated. It's not overly complicated because I do have it factored. Now we could have something already multiplied out and you have to find the zeros. So this could have been a cubic, which you would have to go through all the techniques that we did to factor it, like we did in the beginning parts of chapter 3, and find those zeros, use your P over Q idea and all that stuff. So they could be very complicated problems, but here is one that's already factored. So you might have to do some work to get to this point. But once we have it factored, I know that my zeros are at -1, 3, and -4. So if this were my x-axis, I would have dots at -4. Put some hash marks on here so we can get them all. Let's see, 4, 3, 2, 1. Here's 0. There'd be a dot here, and there'd be a dot here, which is going to divide my x-axis into a bunch of regions. Now this is a cubic. We could talk about end behavior, and we could talk about the y-intercept, and we can do all of that sort of thing. But since all I'm concerned about is it positive above the x-axis or below the x-axis, I'm just going to jump right to a test point. And when I do these test points, I'm not going to be concerned about what is the value, because I'm not graphing it. I don't need the dot on the the graph, I just need to know, am I above the x-axis or below the x-axis? So I'm going to test -5, because that's going to be from this region here. Now, substituting -5 into this first factor, I would get a negative number. Putting it in the second factor, I would get a negative number. And putting it in the third, I would get some sort of negative. Now, a negative times a negative times a negative is negative, which means I'm going to be below that x-axis. I'm going to do the same thing here for a test value between -4 and -1. So maybe -2. Now putting that in here, -2 plus 1 is a negative. -2 minus 3 is a negative. But -2 plus 4 is positive. So this result would be some sort of positive number. I'm going to test somewhere between -1 and 3, maybe 0. So substituting 0 in there, I'd get a positive times a negative times a positive, which the end result would be negative. And we're going to do one more test value up here. Let's say we'll test 5, which gives me a positive times a positive times a positive, which is positive. Okay, I am looking for where my graph is greater than 0 or positive. So I'm looking for this piece and this piece. I am not going to include where it's equal to 0. Now, equal to 0 was at the endpoints. We are not going to include them. So that means my answers are -4 up to -1, so that region there. And then again from 3 to infinity. So I get those entire span of that interval and this complete interval. And the reason this works is because of what we've learned when we're graphing them. We will not be able to go from being positive to negative unless I had a 0 in there. Or in the case of rational functions, which we'll get to later in a different video, is we had asymptotes. And we'll actually put those in here as well on this number line, this x-axis, so to speak. I do want to point out some of those things that we learned about multiplicity. I tested here to be a negative value. This came from a multiplicity of 1, so I would have known it's going to go through at a straight line, which means I had to go from positive to negative. I mean negative to positive, sorry. And then again another multiplicity of 1 and a multiplicity of 1. So it is no surprise that I have this alternating piece. So once you've tested one and you use the multiplicity idea, you kind of can get all the rest of them as well. And I will refer to that as we're going through future examples also. I will do some more examples in a few more videos because again, I like to keep my videos short so that they don't get too long.